Okay, so before we get started, I actually want to ask everyone about the schedule of the office hour. So it occurred to me over the weekend that I actually omit that as with thanks to Jackie, who let me know that my office hour was actually on the exact same time as another, I think, statistic course or something like that. So it was originally 3 to 4 Monday and Wednesday, and yeah, so I didn't know that it was actually on exact the same time as another course, which actually three of the students actually took it. So actually, I have a proposal, and I would like to know that whether it's actually okay for majority of you. So I'm actually thinking moving the office hour from 3 to 4 to 4 to 5. Okay, so as far as I know, that none of you actually were teaching during 4 to 5. I believe what I saw was actually a little bit later than 5 p.m. And also, Ibrahim also told me that there was a functional analysis, like also have an office hour a little bit overlap with my original office hour. So I was actually thinking maybe moving to 4 to 5 would actually be a better case. So does anyone have objection me moving to 4 to 5? If that's the case, let me know right now.
4 to 5 on what days?
Uh, so I was actually thinking both days. So what I also want to know is that whether I want to move both Monday and Wednesday to 4 to 5 or just one of them. Because if someone definitely cannot make it on either Monday or Wednesday 4 to 5, then I can only change one of them, right? So is Monday, Wednesday 4 to 5 okay? For,
That's the time of fluids. I know I have a conflict there.
so
Um,
you mean like there's another class right on Monday, Wednesday 4 to 5?
yes, ma'am.
So
Uh,
from when to when? Can you remind me?
4 to 5:15. It's Dr. DeLillo's fluid dynamics course.
Oh, okay. Yeah, that's the okay. 4 to 5:15. Let me think. Okay, so Jackie, are you here? I think you're here. So so if I'm going to shift just one of the office hour, which one will work for you if I shift to 4 to 5, Monday or Wednesday?
Either one works for me.
Okay, but 4 to 5 works, right?
Yes, thank you.
Okay, so let's do this. So I'm going to shift the office hour of Monday to 4 to 5, and I will keep the Wednesday for 3 to 4, just in case that some of the people may not necessarily like the 4 to 5. Okay, and then I will keep it on, and then we'll see, like because it's just started of the semester, so I'm not sure whether people's schedule really fixed. Maybe later on there's some other things come up. So I'm going to just do so right now change. Oops, let me just write down here. So change Monday office hour to 4 to 5, and I will keep the Wednesday for now. And I will see how many people come. If it turns out that one of the day that people don't show up or something like that, and or then I will change it again. Okay, so I will make announcement. So keep Wednesday 3 to 4. Okay, so hopefully that will fit more people. And then I knew that 3 to 4, I'm not sure, Wednesday 3 to 4 might kind of overlap with functional analysis. So trying to see whether you can work out. And then, for example, if you know that you're going to attend, but you are going to be late or something like that, just email me, let me know. And worst case, I mean, we will still see each other Tuesday and Thursday, right? So you can definitely ask me the homework question after the class as well. That's why I put it on Monday and Wednesday, just to separate from courses, right? And then my homework due is on Friday. So you still have time in between, right? So there's plenty of time. You can actually email me, set up an appointment with me or something like that. Just let me know. So at least I will move one of the office hours so people who actually want to go to the office hour for other courses or took other statistic course can make it. Okay. So just let me know. Yeah, because I actually forgot that people are actually taking courses in different times. So okay, so that's one thing. The other thing is that, okay, so I believe everyone already knew that I posted the homework one, part one. So what I would say is that if you're not familiar with the topology, like some background, then this problem definitely would be a good practice for everyone to review some of the definition and how to work with those definition. I would say it's not that hard as you think, but to really write the solution rigorously down, it takes some time. And so I would say, for example, problem 1, 2, and 3, I would say more or less is by first you need to know the definition or what's the quotient space or product space looks like. And then you need to start from the definition, see whether you can convince yourself, for example, to prove locally Euclidean, can you find a homomorphism from an open set to an open set in R1 or R2, depends on the problem. And I would say the most, the trickier problem would be number 3, the very last one, where I give you the 2 lemmas. And I hope everyone can use those 2 lemmas to prove that the real projective space, RPN, is actually Hausdorff and second countable. So as you can see that, so first week we talk about if you have a subspace equipped with subspace topology, or if you have a product space equipped with product topology. Those two are nice in the sense that if the original space is already Hausdorff or second countable, then it automatically applies to subspace topology or product topology. But it would no longer be the case for quotient space. As you can see from the very first problem, 1.1, you have a quotient space from some nice space, but the quotient space may not be Hausdorff or second countable anymore. And the very last problem is essentially to show you that, oh, if your quotient map, the projection map is open mapping, then it will give you some nice condition. So at least in some spatial situation, the quotient space can be Hausdorff or second countable. And to use lemma 1 and 2 to prove this, you need to do a little bit trick, like you may actually need to create a map. Like for example, one of the lemma says there's a spatial set, I think I denote it as R, need to be closed in order for for the space to be Hausdorff. Then you need to create a function and such that this set R is related to the function, and use this function to create R to be closed, something like that. So I don't want to right away tell you the hints because I think that you can actually think about it. And to be honest, all of these problems are pretty classic in the sense that if you don't want to ask me, you want to Google to kind of learn it yourself, you might already found some information online, right? Those are very classic example that people usually create. So please try your best. And if you have any question, definitely let me know. And if you want me to give you a hint, also let me know or come to the office hour. Okay, so first, so today, hopefully our goal is to go over, I'm going to go over the RPN because we haven't finished. Then we will proceed to some topological properties. Okay, so first of all, I'm going to just recall some of the detail that we know from last time. So some of the definition. So what's n-dimensional real projective space, right? So usually we use RPN, right? So you start from ambient space like the X, right? And it's actually R to the n plus 1, and then you take out the 0, right? Then essentially you can think of RPN is kind of sitting in R to the n plus 1. So initially, it seems like we need to use n plus 1 coordinate to define the equivalent class. But later on, this problem is to prove that this RPN is actually a n-dimensional topological manifold, meaning technically locally, we only need to describe it using n coordinate. So it's actually n-dimensional, okay? So before we do that, we need to define the definition for RPN from using the equivalent class, right? Equivalent relation. So we say that in this space X, we say 2 points in R to the n plus 1 are equivalent if they're like essentially a multiple of each other, right? And as you can imagine, lambda will not be 0, right? Because we take out the origin. So what does that mean? It means if you have 2 points lies on the same line passing the origin, then those 2 points are equivalent, right? Or in other words, later on in the quotient space in the RPN, you should imagine that the element equivalent class essentially is just a line, right? So basically, if you can think of like, maybe let's use R3, right? So we're going to see RP2. So basically, you can see that, okay, I'm going to draw a line passing origin. Sorry, it's a very bad picture, right? So then we say these 2 points, X and Y, are equivalent if they lies on the same line. And this line has to pass through the origin. Or in other words, you can say Y is in the span of X if you want to use the terminology of linear algebra. Okay, so later on in the quotient space, right, after you do the quotient, then you regard Y and X as the same thing, right? That means you regard everything on the same line to be the same thing. So as if a line is just a representative, okay? So then we define this RPN to be the quotient space of X, equipped with the quotient topology given by this projection map. So quotient topology, let me remind you, it means that if you have an open set in RPN, that means the pre-image of this. So basically, let me just say it. So if U in RPN is open, if and only if the pre-image of pi, pre-image under pi of U is open in X. That's essentially the quotient topology. And this map is essentially just the usual projection map in the sense that if you input like any point, right, in R to the n minus 1, not 0, right, then you send it to its equivalent class. Or in other words, you can think of it, send it to the line that it lies in, the line that passing through the origin. Okay, so you give me a point, I give you its equivalent class, the line that it lies in. Okay, so a lot of people actually want rather to think of RPN as a collection of a bunch of line which passing through the origin, right? You can imagine that another equivalent class can be a line like this, right? Anything on this line would be the same thing, or another line passing through origin, right? Or actually any line, right? As long as it passed through the origin. So basically this would, you can think of the equivalent class would be a line, okay? So this is essentially the definition of RPN. So our goal is to prove or show RPN is actually a topological manifold, okay? So let's recall what's a topological manifold. 3 things, right? First of all, you need to be topological space, meaning you need to equip with the topology. You need to specify what topology you're using, right? Because a lot of property actually depends on exactly how you define or what topology you equip, right? If you equip different topology, it may affect the property it carry. For example, I remember we talked about this last week that if you put trivial topology on any space, then it's not Hausdorff anymore, right? And if you put different type of topology, right, you might have different properties. So this is really important that especially at the early stage, when we talk about a bunch of topological property, you need to specify what topology you use. So in this case, we know it's quotient topology that we are using. And other than that, if you already know it's if we have agreed on like what topology we use, then to check whether it's topological manifold, we need 3 things: Hausdorff, second countability, and we need to verify the space is locally Euclidean. Okay, so as you already knew that the first 2 parts, Hausdorff, second countability, is the homework problem. So I will let you work on this over these 2 weeks. And last time we start to prove whether this is a locally Euclidean, right? And I already kind of tell you that the answer that is supposed to be a n-dimensional manifold. That means it's locally homeomorphic to Rn, right? The dimension is very important because actually you can create some weird example that based on the different topology you put or you impose, sometimes that the same space can be locally Euclidean, or you should say locally homomorphic to R1, or actually possibly R2 locally, right? So the thing is that it depends on the topology you put, okay? If you create some bad example, like it might affect the whole thing. Okay, so now let's see. So I think last time, I think we also talked about this. So let me just briefly review. So first we need to find out what's the open set that we need, right? So most of time for a quotient space, we want to start with the original space X, because sometimes it's very hard to directly describe whether a set in the quotient space is open or not. And in other words, because we're using quotient topology, right, it kind of boils down to what's the pre-image looks like in the original ambient space. So sometimes it's easier, we start with working with an open set in X rather than the quotient space. So we use this, I'm trying to use the same notation as textbook, so later on it's easier for you to review. So we define for I from 1 to n plus 1, we define this UI delta to be an open set in X, right? This is X. And this open set essentially is the collection of all the points where Xi is not 0, okay? Because later on, you're going to see that this is essentially like we need to take n plus 1 open set in order to cover everything, okay? So now the open set we really need on RPN is the image of this UI delta under the projection map. So this is the UI, the coordinate domain that we need later on. And so this is basically the image of UI delta, and it essentially it lies in the RPN, right? So what I want to show is that this is actually an open set, right? Because that's what we need, right? We need to prove that quote the RPN, you need to create a homeomorphism from this open set UI to another open set, right? You need to define or essentially find the homomorphism, and you also need an open set, okay? So how do I say or prove that at least I need to convince myself that this UI is an open set? Like there's several ways to view it, right? Intuitively, geometrically, you can think about what this UI looks like, right? So UI delta is all the points such that Xi is not 0, okay? Then if you draw the picture, right? And then if you put, say, okay, this is my, that's called the last axis, that means denote it as Xi, okay? Essentially think of, like, if you don't feel comfortable putting Xi as that coordinate, just think of Xn plus 1, right? Just pick one of them. And this is the remaining Rn, right? So this is, the whole thing is Rn plus 1, right? So I put Xi to be the Z coordinate, so it's better for me to view. So this is when, so what's when Xi is not 0? So it's anything but the plane, right? The bottom plane. So then if you send it through pi to the quotient space, then what does it look like? Then essentially you want a whole bunch of line which does not lie on the flat plane, right? You don't want the one lying on Xi equals 0. So you're essentially geometrically, UI, this open set describe the collection of all the lines that which does not lie on Xi equals 0 plane, right? So which means that if I'm trying to draw a nice picture. This dotted line is something I don't want on the plane, right? I don't want this line, right? So any other lines, as long as it's not lies on the, XY plane in the picture, then we are fine, right? So this is essentially geometrically. So you can think of that it's in some sense an open set, right? You're taking a collection of all the lines other than the one lies on the flat plane, the floor. But it's not rigorous, right? So we want to rigorous prove it. Okay, so let's see. So this is actually not like, if you want to really rigorously say it, you need to do some work. So first of all, we realize that if you actually, this is something you need to check. You can actually easily prove it just by using the definition. So you can check that ui tilde is actually the same as pi of ui, and then you plug in pi of ui into the pre-image. So in other words, this is what we call saturated set. What's a saturated set? Means it's the pre-image of some set. Okay, so you can see that if you code this V, then it's pre-image of V, pi inverse of V. So it's a saturated set. This is some definition we mentioned last week. Not only it's saturated set, it's actually an open set. Okay, I mean, just from the definition of ui tilde, you know it's open. Okay, so this is perfect because the fact that itself ui tilde is open, plus it's the pre-image of some set, then this automatically imply that ui is open, right? Because this is essentially from, by the definition of quotient topology. Actually, this is ui tilde, sorry, quotient topology, right? So because we said what's an open set in RPN, as long as its pre-image is open, right? So we already know ui tilde is open, right? It's the pre-image of pi of ui tilde. So by quotient topology, this tells me that pi of ui tilde, which is essentially ui, is open, right? Just by the definition of quotient topology. Okay, so that's why I assign quite a few homework problems related to quotient space, because I want to make sure everyone get to practice about the quotient space, because this is usually a little bit hard, sometimes a little bit hard to visualize, and also to see how to use all this work with definition. Okay, so now we convince this ui is open, and that's going to be our coordinate domain. Then we need to create a homeomorphism. Okay, so now this is something that I need to be a little bit cheating, in the sense that, like, I'm going to use some theorem from the appendix. So we already know pi itself from X to the quotient space is a quotient map, right? But we don't know whether, if we restrict it in a subset, whether it's still quotient map or not. Remember, quotient map has certain criteria you need to satisfy. It needs to be surjective, continuous, and also the target space should be equipped with quotient topology, right? That's a quotient map. So it turns out that if your subset is a saturated open set, which is the case in our case, saturated open, then from the theorem in the appendix, it tells you when you take the quotient map restricted in or on a saturated open set, then this new map will still be a quotient map. Okay, this is not that obvious. You actually need to kind of just prove it a little bit. So you can actually see that this is the theorem I'm going to quote. So you might wonder why I care about this pi restricting in on ui tilde to be a quotient map, because later on, I'm going to use this to prove that the map phi I define here is continuous. So because I need to go through the quotient map, this is the characteristic property that I mentioned last time. Okay, so now let's see. So I'm going to define this VI that I hope I can prove it's a homomorphism eventually. So this map should be from RPN, right? And this is from UI, essentially this open set that we already proved that it's open set to Rn, right? And the definition is the following. If you give me an equivalent class from RPN, right, using n+1 coordinate, then I'm going to turn it into something with only n coordinate. And because you can see that what's the definition of UI, that's when xi is not zero, right? All the lines when xi is not zero. So you can see that, okay, then I can like I can do the legit action that divide by xi. So the only thing you need to be careful is that once you reach I minus 1's coordinate, you jump to I plus 1, right? So this is definitely a point in Rn, right? That's the whole point. We want to prove that it's homeomorphic to Rn, right? But whenever you define a map from a quotient space to somewhere, you need to be careful this map is actually well defined, right? Because you are actually input an equivalent class. So you don't want the bad things to happen where you input 2 points where are equivalent, but they map to different thing. Then your map would be not even well defined. So if you already read the textbook, you will see that they actually, the very first thing after they define phi, they need to check this map is at least well defined before you can even prove it's continuous. Okay, so how do we check it's well defined? As I said, you want to show that two equivalent points in the same equivalent class should map to the same thing, right? So in other words, mathematically, it's what I show here. You want to say that, okay, if I plug in this line represented by x into phi, it should be the same if I plug in y, if you call lambda x to be y, meaning any equivalent point. Then this whole thing, right, these two things should be equal. But this is not hard to check, right? One of them has the coordinate x1, x2 to x n plus 1. The other has the coordinate lambda x1, lambda x2, to lambda x n plus 1. You can see that this map phi that I define here, since you're going to divide xi anyway. So say the first coordinate, you have lambda x1 divided by lambda xi. So the lambda will cancel out each other. So eventually you will still only get x1 over xi. So it's not going to change anymore under the scaling, okay? So that's why it's a well-defined map from the equivalent class. That's the first thing we need to be careful. Now, after this map is well-defined, then we see, okay, whether we can prove it's continuous. And you might wondering, okay, what's so hard proving continuous that require us to go through the quotient map? Because you can see that your input is not really just R to the n plus 1. Your input, your domain is actually some quotient space, right? The quotient space is quite different from the original space X, right? So you cannot just directly look at the map, say, oh, it's continuous, right? You actually need to use topology to prove it, but sometimes it can be hard. So usually when people work with a quotient space, they use this, the characteristic property. Okay, so this is something we talked about earlier. So characteristic property, usually we use this kind of diagram here. So first, this is exactly where the quotient map come into play. So you have something from X, right? Or you can say RP, R to the n minus 1, take out 0, right? And you map it to something in RPN, okay? And you have this phi I that we don't know whether it's continuous or not. That's what we want to prove. But the characteristic property of the quotient map tells you if you already have this quotient map pi here, and you have another phi like this, then if you want to prove phi is continuous, the only thing you need to show is this phi composed with pi is continuous, or vice versa. Let's say if you want to prove, I mean, vice versa is actually easier, right? We already know if phi is continuous, if pi is continuous, then the composition is continuous, right? So the other way is actually easy to prove. So now, as long as we can, so we want to show that this is continuous. And it's actually easier to see, right? Why? Because phi compose pi, you can see what's the domain and target. It's from R to the n plus 1 to Rn. Those are the things that we usually see all the time, right? We can easily tell that whether a map from some Euclidean space to Euclidean space is continuous or not, because the topology is the usual topology we work with, not something weird, quotient or some other thing, right? So usually if you don't know whether a map from some spatial space or manifold to another space is continuous or differentiable later on, you're usually trying to lift it, or we say pull back, depends on how you say it, to Euclidean space. Okay, so now let's see what would be this map looks like, the Phi composed pi. So Phi composed pi, when you restrict it to this set, it's Ui delta lies in X and mapping to Rn, right? So this essentially tells you the map looks like you plug in x1 to x to the n plus 1, you have n plus 1 coordinate, right? And you can see from pi, so first you plug in into pi, it gives you all the equivalent, the same equivalent class. But after you go through Phi, essentially you divide it by xi, right? So essentially the map is x1 over xi, x2 over xi, all the way, and this is xi minus 1 of xi, xi plus 1 over xi, till x to the n plus 1 over xi. So actually, I'm breaking down into step by step so you can easily see. So this is the Phi of pi, right? So I mean, forget about the middle step, right? I just want to show you it's really indeed like this. So you can see that if you are in the domain where xi is not 0, right? We already know xi is not 0 because it's in Ui delta. And you tell me what's the map, whether the map, you can see the map is from x1 to xn plus 1 to this whole thing, right? Since xi is not 0, so it's definitely continuous, right? This is just you use the usual sense for the advanced calc, right? This type of map is continuous because, I mean, each coordinate, each component function is continuous, as you can see, right? So now we are convinced this Phi of pi is continuous. Then by what I just said, the characteristic property of the quotient map, because this Phi composed pi is continuous, then Phi is continuous. So we just confirm that we do have a continuous map for now, mapping from an open set RPN map to Rn. So now the question is, okay, we're almost done. We still need a inverse map, and we need the inverse map to be continuous. Okay, so first I need to tell you what would be the inverse map looks like, right? So the inverse map exists, and I can actually tell you it's defined by the following. Okay, so first let me be specific about the domain. So this is from Rn, right? Back to Ui, which is in RPN. Okay, and I can explicitly write down the coordinate here. So I map from Rn, so there's n coordinate, back to the equivalent class. Okay, so equivalent class should have n plus 1 coordinate here. Oops. So I need to create one extra thing. Okay, so now let me specify how does this map works. You plug in whatever n coordinate from.
Should that be Ui plus 1?
No, actually it's Ui. Yeah, because actually essentially I stock 1 on the i's position.
Got it. Thank you.
Yeah, perfect. Okay. Yeah, you want to be very careful sometimes that, yeah, like you might make a mistake. So it's a little bit different than the phi, right? It's actually Phi inverse. So it's a little bit different. So what it is that, okay, you somehow need to make sense, right? You need to like create a extra coordinate here. So what they really map is you give me n coordinate and I'm going to stock like a extra 1 here in the i's position, depends on what I you pick here. Okay, of course, you might ask me that how do I know this is the right map, right? Of course, I'm going to leave, this is not hard to check. With this definition, I'm going to leave you as an exercise. That is not bad to check. And I think it's a good exercise for you to work with the RPN definition. You want to show that VI inverse defined this way is indeed the inverse map of VI. Okay, so how do you check? Essentially, what you want to show is that you compose UI inverse and VI inverse and VI. It's really identity map. And you also want to show the other way around is also identity. So in other words, if you start from Rn, or I mean, depends on where, if you start from Rn and you go through the VI inverse and come back, you want to show that it's really get back to yourself. And you can see that this is going to definitely work because how we define the VI and VI inverse this way. Okay, so I'm going to leave you as exercise to really show that this is the correct inverse map. Okay, but now the question is kind of appeared again that, okay, even though now my domain is for VI inverse is in Rn, but now the target is in RPN. So it's still not that obvious whether it's continuous or not, right? So because RPN has some spatial topology. So again, we need to actually try to see that whether it's continuous or not, okay? So first of all, before we prove that, I want to show you geometrically what does this map means between VI and VI inverse, okay? So in this case, I use this, I call this U to be like all this point to be just a point U here, okay? So I want to see that if I want to go through VI and then VI inverse, what's the relation between all these points, okay? So if we define this way, so actually this is also in the textbook, I just kind of copied down here. So geometrically, phi is our coordinate map RPN to Rn, right? Okay, so you map an equivalent class, let's say X, to some coordinate or points in Rn. Geometrically, what does that mean, right? So you give me a line in R to the n plus 1. You want to map to a point in Rn. Which point should it map to, right? Geometrically. That means, okay, if you look at this picture here, and again, I put, actually, I should put VI here, sorry, right? So I put X to the I, like the I's coordinate as my Z axis, so I can easily visualize it. So geometrically, if I say through VI, I map this line, which is the equivalent class of X to U, then what's U here? It turns out that, okay, if this red line you saw here is the X coordinate, the line, the equivalent class, U will be the projection point of this U1. So this is in Rn. So what does that mean? It means if you take this line, intersect the hyperplane when xi equals 1. If you intersect with the plane xi to the equals 1, you will have an intersection. This intersection is essentially U1. This is actually a bad notation. It's really just say U1, U2, and then you stuck 1 in the i's coordinate. This is exactly what Jackie just asked me, the coordinate that we have here. And the U essentially means that everything else, you take out the 1. That's the projection map onto the other n's coordinate, right? So essentially, if you send through VI, if you send this line to U, that means U with the extra 1 here would be the intersection point of this line with the hyperplane xi equals 1. So that's the kind of the geometric picture here. Okay, so that's why you guarantee later on when you plug in back to say VI inverse, it's going to get back to the same thing, to the original thing. So that really gives you the correct inverse map. So now this is geometric picture. the very last thing we need to do is to convince ourselves that phi inverse is really, actually I keep forgetting about the I here. Phi inverse is really continuous. Okay, so now let's see. This is, I'm not sure whether this is actually included in the textbook, so I actually filled in some detail here because I think it doesn't necessarily like actually provide every single detail. So phi inverse, you observe that it's actually pi, the quotient map, composed with fi. What's fi here? Fi is really just sending the u, the n coordinate, to another n plus 1. This is not in quotient space, okay? So be careful trying to distinguish with phi inverse, right? Phi inverse is sending points in Rn to a equivalent class in Rpn, right? And Fi is just sending a point in Rn to R to the n plus 1, not the equivalent class yet. Okay, so be careful here. But as you can see, once you define such Fi, then you're plugging into pi, right? If you're plugging into pi, let me do it here. If you're plugging into pi, that will give you the real correct equivalent class, right? So you can see that that's how we find out phi inverse, or how we rewrite phi inverse. And if you can accept that phi inverse is nothing else but pi composed with fi, then you can see that fi is continuous, right? It's just some usual map from Rn to R to the n plus 1. And pi as a quotient map, it's already automatically continuous. So you have continuous map, composed continuous map. So of course, we know that phi inverse is continuous. So you can see that we usually trying to avoid directly working with equivalent class or quotient space, right? Because it's hard to describe what would be the open set or the map looks like. So we kind of go through the pi most of the time. Now we have phi continuous, and we have an inverse map, phi inverse, and we also know the inverse is continuous. So this is really a homeomorphism mapping from the open set UI, right? So this is the homeomorphism we want. So we prove that it's locally Euclidean, okay? And to be precise, it's locally looks like an Rn. So now the only thing we need to kind of address it at the very end is that all the UI we found really cover every single point on RPN, right? This is kind of obvious, right? Because the definition of UI, right? It's all the lines except the one that xi equals 0, right? So this UI is definitely cover everything on RPN, right? And so that's why for each point, we can find such UI, which is locally homomorphic to Rn. So this proof RPN is locally Euclidean to Rn. And that's how we prove the RPN to be topological manifold. So I spent quite a, sorry, I heard something. Question?
I have a question, Professor.
Yeah.
So
Yeah.
So the inverse is continuous because I mean phi inverse is continuous because I'm not getting why it's continuous. Is it something that we have done before in the surfaces that the function of a function is continuous? This means that the inverse is continuous.
So phi inverse is continuous because we realize that phi inverse is really a composition of pi and this fi I created here.
And each one is continuous.
And both of them are continuous, fi and pi, because fi is just mapping n coordinate here from Rn to u1 to ui minus 1, 1 in the i's position and all this, right? So you can see that this is like, if based on what we know before, the knowledge from advanced calculus, right? If you plug in u1 to u1 and then all this coordinate here, this is definitely a continuous map, right? From some analysis course, because this is a usual map from Euclidean space to another Euclidean space, right? So this is so Fi by its construction is continuous, and pi is the quotient map that we know of. So quotient map by definition of quotient map is also continuous. So I'm using the fact that the composition of two continuous map is again continuous. Of course, I mean, if I can definitely prove it, right, using like open set using topology, but I'm trying to just take it for granted because we kind of already know the composition of two continuous function should be continuous. Does that answer your question?
Yeah, but in like in exams, we don't have to prove like each one is continuous. We can say like by fact it's continuous, or should we go through the?
No. Actually, the thing is that if you don't write me like Phi inverse to looks like pi of Fi, then how do you know it's continuous? Because the thing is that the fact that if you go back to see the definition of Phi inverse, it actually map a point to an equivalent class, not a point. So you can, if you look at Phi inverse, it's from Rn, which we understand very well, but the target is in Rpn, which is the output is an equivalent class, right? So it's actually not obvious that this map is going to be continuous.
I see. Yeah.
Yeah, because like the quotient space works a little bit different, right? You need to really prove that, oh, you really pull back the open set to open set. And now you need to work with the open set in RPN. So it gets really messy. So that's why I said that usually we're trying to avoid working with the equivalent class, but we kind of detour a little bit. Yeah. This is actually kind of going down to the very detail, like everything start from the scratch. Intuitively, it's definitely continuous if you think about it, but we want to write it down more rigorously. Yeah.
Thank you.
Oh, yeah. Okay. So now I want to also tell you an extra like a remark that it turns out that the way we define RPN is not or how to say the definition of RPN is not the only way to define it. There's another actually quite popular alternative definition that people usually do. Okay, so let's go back to think about how we define RPN. The original way we define it is that, okay, we take out everything in R to the n plus 1 besides 0. Okay, we don't care about 0. And we defined two things are equivalent if there are lights on the same line. Then we essentially have a collection of a bunch of lines. Okay, so that's the usual way. But if you think about it, do we really have to use all the points in R to the n plus 1? Not necessary, right? So as long as we can somehow identify such line, right, then we don't really need to use the whole R to the n plus 1. So it turns out that we can use sphere to define RPN. And this is actually, in some sense, actually a better way to define it, because sphere is something that we know much better in some sense, right? And then, so basically, and then Sn is a subspace in R to the n plus 1 as well. So this alternative definition, I think the textbook doesn't include it, but I think it's a nice extra thing in geometry. So now instead of doing x, take the quotient of x, we take the quotient of sphere. So what would be the relation, equivalence relation that we want to use? So our ambient space becomes the sphere, n-dimensional sphere. And we say 2 points on the sphere is equivalent if y equals minus x. So that means y is the antipodal point of x, meaning they're opposite position of each other, right? In the sphere, you always can find a unique antipodal point. Then you take the quotient space of this sphere under this equivalent class, then it will still give you the same thing. So geometrically, let's think about the picture here. Let's say you have Sn, right? Okay, that's 2S2, or you can think of Sn, right? And you have and you can see that if we define our ambient space to be on Sn, then we don't need to worry about taking out the origin, because origin is not on the sphere anyway. And we say 2 points are equivalent if they are antipodal point to each other. So how do you draw antipodal point? You essentially draw a line passing through origin. So you can see that implicitly, we're actually doing the same thing. We're trying to identify things on the same line to be equivalent. but only if now, because we're restricted on sphere, so we only have 2 points, which are the antipodal points. So you can see that, okay, this is the y. So we identified these 2 points, right? So you can see that it should describe the same space, right? So this, if we take the quotient map from Sn to Sn quotient, and I mean, we use the same thing, right? You send the points in Sn to its equivalent class under this equivalent relation, then we are going to see, you can actually check or show. It takes some time to show it, but my point is that under this Sn to the quotient, this new quotient space is actually homeomorphic to Rpn. They're the same thing. Okay, right? If you think about it, right, we actually identify points, antipodal points, to be the same. So we essentially implicitly are thinking anything lying on the same line are the same. So in some sense, we are still doing the collection of all different lines. So essentially, we abandon R to the n plus 1. We actually just use Sn, it's enough. So this is actually other way of thinking about RPN. And you probably, if you read some other literature, you probably already see it. Sometimes people actually likes to work with this definition rather than the original one we saw. But I think you should know both, okay? So this is actually just an extra information. So now I want to go to introduce some topological property, but as you are going to see, I'm not going to prove too much about this because I have this feeling that, first of all, most of the proof, or I mean, most of the lemma or proposition or theorem, I'm going to show you the statement. They're all in the textbook. And then the difficult one, actually, the proof is already in the textbook. And I feel like that instead of me spending half an hour repeating the proof, and it's very hard to understand right away. So the better way is actually for everyone to read the proof by yourself, because there's a lot of detail you need to really think about it by yourself. You're not going to understand just by listening to what I said. So I'd rather skip that detail, but just to tell you what's the key point here, okay? And the topological property that we are going to see here, most of them, we are going to use it later on in chapter 2 when we're trying to construct what we call the partition of unity, okay? So by some of the things that I want to recall as a review as well. So we say a subset in the topological space is pre-compact if the closure is compact in X. Okay, that's just a definition, like pre-compact, okay? And it turns out that as a topological manifold, we have a nice property that not only, I mean, because it's second countable, we already know it has countable bases, but here we have a slightly stronger property. We actually have a countable basis of pre-compact coordinate both, okay? So what's coordinate both? It means that this neighborhood, this open set, is going to be homomorphic to a ball in Rn, right? Because we have this coordinate map, the homomorphism, right? So we say it's coordinate ball, meaning that it's actually homomorphic to a ball in Rn through the coordinate map, through that homomorphism that we know, okay? And on top of that, we also know it's pre-compact, okay? So I'm going to try to do a quick sketch of the proof. As I said, the proof is actually already in the textbook, but I'm going to tell you a quick idea about how to prove this thing. And it actually kind of separate into case 1 and case 2. Case 1, so first of all, we know M is a topological manifold, okay? Case 1 is if M can directly covered by one single coordinate chart, right? Meaning you only need one open set U, for example, to cover everything. For example, like Rn, right? You can just directly take the, I mean, Rn is kind of too trivial, not interesting, but it's an easy example, right? If you can imagine, how do you prove Rn is locally Euclidean? You just take the whole Rn as an open set, and you even can take identity map, right, then it's definitely homomorphism. So Rn is kind of the most trivial situation where it can be directly covered by a single chart. But for example, when we work with sphere, right, you need more charts to open set to cover it, right? So this is not the case. Okay. So first we do the case one where the manifold can possibly cover by one single chart, one open set. Then this is easy. Then once we can prove the lemma 1.10, then we go on to prove the case two is when M is covered by countable many open sets, right? Countable many coordinate domain. Then in some sense, in each coordinate domain, it becomes back to the case one in some sense. Okay, so that's the scheme. So first of all, let's see how do we prove this, right? So the goal is to prove that it has countable basis of pre-compact coordinate balls. So not only you want to show that this open set is going to be mapped through the homomorphism to a ball, you also want to show that its closure is compact, right? So now let's see, like I'm just going to kind of just do the sketch of the picture, right? So let's say your manifold M, right, can be covered by a single chart, right? So that means like M is the open set that you know, right? This is open, just single chart, right? You can cover everything by a single chart. And you have this phi is the homeomorphism that we know of. This is the coordinate map, okay? And you map to some open set in Rn, right? That's coded UI head, and this is in Rn, right? So let's say you only need one single chart, okay? So now the whole point is we need it to be countable, right? So I keep the lemma 1.10. You want a countable basis, right? In Rn, we already know there's a free countable basis, right? Remember we talked about Rn being second countable. What would be the countable basis? We pick all these open ball centered at those points with rational number coordinate, rational coordinate, also with rational radius, right? Those are the one going to give us a countable basis. So you take all the open ball with rational center and rational radius, and you do the collection of all of them. It's going to be a countable basis, right? Because rational number is countable. So basically what we're going to do is, in roughly speaking, I'm going to do a very sketch of the proof. You want to collect all the open ball in this open set you had, and this open ball essentially is those one that I just said, right? With rational center, and R is the rational radius, right? I'm going to do a bunch of collection of all these things. You can always pick out so many ball like this, and then we want this ball to be strictly like content in this open set. Okay, so that's the idea. You can definitely collect all these things. And this is a collection of countable stuff, right? Because how we pick it. Now, what we're going to do, right? First of all, it's an open ball in Rn that we know. So we already know from the earlier knowledge of topology, right? If you take the closure, which is essentially the closed ball, right? This is compact in Rn, right? So definitely compact in UI head as well, right? I mean, from some of, that's why you need the advanced calculus. We know that the closed ball in Rn is going to be compact, right? This is something, I don't want to reprove it, right? This is something we know of. So now we want to use this fact and see how we can create all this pre-compact open set back in M. So we can do it through the phi inverse, right? Now we say, okay, we map back here, right? So we have some other open set here. This is essentially the phi inverse of this ball, right? And because on the right hand side we have countable many of them, right? So if you map it back through phi inverse, there's only also countable many. So now the question is, and this actually is what we call the coordinate ball, right? Because it maps to a ball in Rn, right? So this is already a coordinate ball. So the only thing we need to prove is it's actually pre-compact, meaning if you take the closure of this open set in M, is it going to be a compact set, right? But then we are going to use this, I would say a set theory or topology in some sense. This is key, right? If you take the closure of this set, you can actually check that this is going to be the same as the pre-image, or actually the inverse of the closed ball. You can actually check that because phi is actually a homomorphism. And even better, if you can, if we know these things, then we're already done, because you already know that this closed ball is compact, right? And phi inverse is also continuous because it's a homomorphism. Phi is a I think in advanced calc, I believe that this is one part of the advanced calc saying that if you plug in a compact set into a continuous map, the image is going to be continuous as well. If your map is continuous, right? Sorry, image is going to be compact if the map is continuous, right? So because phi inverse is continuous and you plug in a compact set, so this tells me this closure of this set is compact, meaning the open set we just found is pre-compact, right? So this means is pre-compact in M, right? So we actually know that each such ball or such coordinate ball is pre-compact, and we have countable many of them, right? And then you can actually check that, I mean, because on the right-hand side, it's going to cover all the UI head, U head, right? So when you plug in back, it's going to cover all the M. So it's going to be our basis. So this is actually a rough idea. I mean, will be the picture you're going to see or you're going to draw when you read the proof. So now what about the case 2, right? If M can be covered by a single chart like this, then it's easy. We just need to work with this one particular open set. But you can imagine it's going to be the same if it has more than one coordinate domain, right? Coordinate chart. So the idea is, okay, within one single chart, you have countable bases like this already. If I can guarantee that I only need countable many chart, then you're essentially taking countable union of some countable collection. It will still be countable. Then we're good, right? So the only thing we kind of need here is that we need a count. We want only countable chart. Okay, then we are kind of done. So case 2 is not too bad in the sense that, okay, now if M is second countable, is topological manifold, right? Then any open covering, right, it's going to have a countable subcovering, right? So let's say originally you have more than countable open charts, right? And those things is going to form an open covering of your space, right? Let's say you originally you have so many charts or like coordinate domain that union to be M, but you don't know, you're not sure whether they're countable or not. But at least this will be our open covering. But since it's this is actually a property I use. This is actually a property I use. I forgot what's the theorem in the appendix. You can actually prove that if you have a second countable space, any open covering is going to have a countable subcovering. So essentially, from this coordinate chart, we can actually pick out countable subcovering such that it will still cover the whole M, okay? So then you essentially you only need countable many chart. And each one is the case one we just did, right? So M can be covered by countable coordinate chart, right? And then it actually kind of back to case one. Back to case one, right? So each coordinate chart, you have countable bases of pre-compact coordinate ball, but you have countable many of them. So you union all of them, it will still be a countable collection. But the only thing I need to give you a warning is that in the very end of the proof, that you need to be careful, right? Those from the case one, those coordinate ball we proved to be pre-compact. The closure is compact in each coordinate, right? So you need to kind of address it and do a little bit more work to show that the closure of a subset is actually a closure of an ambient set. It's a little bit different, okay? So I'm going to just, I don't want to say too much because if you haven't seen the proof, it's going to confuse you and you don't know the subtlety here. So I would say, please just read the proof later on by yourself. You're going to see that at the very end of the case two, you need to justify a little bit more. But the idea is the following. It's more or less like what I draw here. You start with single chart. You take care of the single chart. Then for your general case, if you can convince yourself that you only need countable many coordinate charts to cover everything, then we're done. Okay, so that's the concept here. Okay, so I think the last couple thing I want to show you is just this, proposition 1.11. So if you cannot, I know that I pre-write a lot of things, so maybe sometimes it's hard for you to write down everything. So I don't want people to worry having to copy down everything because most of the thing I really just follow by the textbook. And I just want to show you these things exist. That's why I pre-write down, and then everything is the same as the textbook. So let's say we have a topological space X, and let's recall the definition for the space to be locally path connected. Okay, so first we need to recall our, I believe you already heard what's connected and path connected, right? I'm not going to repeat it. You can easily find a definition yourself. Path connected means any 2 points in the space can be joined by a continuous path, right? This is path connected. But what about locally path connected? Locally means that you have a basis of path connected open set. In other words, at each point, right, locally, it's just local, right? If you have a manifold, maybe behave a little bit bad, right? But locally, for every point P, you can always find an open set such that in this open set is path connected. This is roughly speaking the definition for locally path connected. It turns out that if you have a space or a manifold which is locally path connected, then the concept about connected and path connected will be equivalent. So first of all, you should realize that path connected and connected are two different things. Okay, so first of all, this is a remark I want to make here.
Question real fast.
Sure. Mm-hmm.
When you said path connected, you said that it has to be a continuous path in say X.
Yeah, in X. Yeah.
So okay, just the book just said a path. So
usually I think the path that define the path to be a continuous map. Continuous function. Yeah, in some, yeah. Okay, so correct me if I'm wrong. I'm trying to remember a lot of definition now, but I remember path has to be continuous. Yeah. Okay. And so here I want to give you a remark that path connected and connected are two different things. First of all, path connected would imply connected. This in the topological space, you can prove that. But not the other way around, okay? Not vice versa, okay? You have a space that might be connected, but not path connected. Okay, so connected, the definition is that you cannot separate the space into two disjoint open set, right? So the classic counter example is what we call the topologist sine curve. Okay, I think I need a little bit space here to just roughly draw the picture. So give me a second. Okay, so I want to give you this weird space or the graph. Okay, you can actually just Google the name like topologist sine curve. Okay, so the picture, the space looks very weird. So at 0, it's 0. And it's like, it's a sine curve, but since you have 1 over x, so it's like very, very isolated very much. Actually, this is a very bad picture. It never reached 0, actually, but it oscillates so much. So you can see that why it's connected, because it was so dense, you cannot separate it using open set. But it never reached to the 0, right? So you cannot connect using any continuous function, any path to connect any points from outside to the origin, because it oscillates too much, it never reached 0. So it's not path connected, but it's still connected. So this is actually a very typical classic example for a counter example, a space to be connected, but not path connected. So those two are different. But this proposition actually tells us that if you have a topological manifold, then first of all, this manifold will be locally path connected. Once you have locally path connected, then actually you will actually can tell or say or actually prove that under this situation, connected and path connected will be equivalent. Okay, so it's not always true unless your manifold is already locally path connected to start with. And because of that, then if connected and path connected are equivalent under this situation, then their corresponding component will also be the same. So the connected component of the manifold will also be the same as the path connected component. Actually, I forgot a word here, path connected component. And also on top of that, we can also prove that in this case, M can only have countably many components, right? And each of them will be an open set and connected, right? You can imagine each of the component, if you union together, it should be an open set. Open covering. But we know topological manifold is second countable, so it should have countable subcovering. So you should only have countable many components, right? Because all these components union together will be an open cover. So that's essentially the rough idea that why we like topological manifold, because with topological manifold, we automatically have all the nice property, right? You actually right away know if I see this is connected, it's automatically path connected, okay? Because it's topological manifold and we have all this nice property. Okay, so the last thing, I don't think I can have time, but I just want to give you like a preview that I'm going to, so essentially, let me quickly review this. So we said topological space is locally compact, right? This is another definition. If for each point in the topological space, you can find a neighborhood, open neighborhood actually, U of each point, such that it's contained in a compact subset of X. Okay, that means it's locally compact, right? So for each point P, you can find an open set, open neighborhood, such that it's contained in a compact set. So that's locally compact. And actually by lemma 1.10, you can actually prove each topological manifold is already locally compact. It may not be compact, right? We know that you can find a non-compact situation, but each topological manifold would be locally compact. For example, just think of Rn. Rn is not compact, definitely not, right? But it's locally compact because each point you can find an open neighborhood content in another closed ball, right, which is compact. So you can, whenever you want to use some examples, think of Rn, right? So I'm going to stop here. I will come back to see, like, if I have time, I would go over some of the propositions. So I still have some of the topological property that I left. So I'm going to just quickly go over the definition here because we're going to use it in chapter 2. So I want to show you. And then after this, after theorem 1.15, I'm not going to prove it, but I'm just going to show you the statement and draw the sketch of the picture. Then I will move on to the smooth structure, right? So how can we define smooth structure? Then we will use it to define smooth manifold, and I will talk about example. So I'm still a little bit slow here. So please read in advance so you can kind of know that what to expect. So let me know if I have any questions. Otherwise, you're free to go. Thank you.
I actually had a question about the homework.
Yeah, sure.
So let me pull it up real fast. So I feel kind of, I don't know, like, just my problem for problem 1.1 is, I guess I don't really understand what it's, like, how to set it up.
Okay, so first you need to know that what would be the map, the space looks like. So
Yeah.
let me go back to somewhere else so I can pull up a new thing. So, okay, so if I remember correctly, they want to identify, they're in R2. And
such that y is equal to plus or minus 1.
yeah, so x is just 2 lines. I'm going to just draw the picture. 2 lines. One is y equals 1. One is y equals minus 1, right?
Okay. Yeah. Yeah.
Yeah,
Gee.
right. It's just R. So you need to draw the picture. This type of
Yeah.
topological problem, you need to draw the picture and you need to got the correct picture. So what they means is that, okay, I'm going to identify, right? Equivalence relation means you want to identify things. So I'm going to identify points on these 2 lines. And you can see that they said that 2 points are equivalent when only when x is not 0, right? So that means, okay, so I need to point it out the 2 origin here. So let me code, I mean, that's why they code it lines with 2 origin. So I'm going to say this 0, 1 points here. I'm going to use a lazy notation. I'm going to code it origin on y equals 1. And this is 0, minus 1, and I called it 0 sub minus 1. Okay, so the equivalence relation actually tells you I'm going to identify any points here with the same point down here. So these 2 are equivalent, right? Or here with here, right? The only thing I don't want it to be the same is this 2 origin. Other than that, everything else is equivalent. So if you think of that, the points here, you can think of these 2 points are equal, like as if it's one thing, one same thing. So then after you do this equivalence, like quotient, what would be the quotient space looks like geometrically? It actually looks like as if you smash 2 lines to the same line, right? But then the only thing you left is the 2 origin that you cannot identify. Right? So basically, yeah, so it looks like a little bit weird, like everything up to origin looks like R in R1 real line, but you have 2 origin. So let me just put 2 origin here. So that's essentially geometrically what it looks like.
Okay.
Yeah, so
And
if
then-
you, yeah, go ahead, sorry.
I was just gonna say, when it says, so when it says let m be the quotient of x by the equivalence relation, when, like, just me trying to write it out, so it would be like m is equal to, and then x divided by and then the equivalent, like that.
This is
That
what we
right there,
call
what
the
you just wrote?
quotient. Yeah, this is the quotient space. This is usually essentially so M is really just this space. This is
Okay.
a topological space. Yeah.
And then that tilde is represented by the
By the
x comma
equivalence.
negative. Okay. Yeah, I was trying to like write that out, and I was like, I don't know. It's kind of weird. I did the x divided, and then I did x comma negative 1, and I was like, this doesn't look right. So
So what? Okay, I'm not sure I 100% get you. So you just worry about the notation, or what do you mean?
yeah,
Like,
but drawing this out really helped because, man, I did not.
yeah. So another crucial thing here is that now because you want to prove that it's, say, not house stove, but then second countable or locally Euclidean, you need to be able to describe what would be the open set looks like in this space.
Mhm.
Okay, so yeah, you need to use quotient topology for this space. So essentially, quotient topology means that you have a projection map, right, from X, which is the two lines, right, in R2, and map to this M here, right? And this is just, if you give me a point, I map to its equivalent class, right? And the quotient topology means if U in this set is open, so the definition is U is open in this new space if and only if the preimage of this thing is open in X, right? So then this means to understand what a typical open set in this weird space, you need to understand what would be a typical open set in the original two lines looks like, right?
Yeah.
So that's C, right? Originally, if you only have two lines lying in R2, right? So we can use the subspace topology. So subspace topology means just take an open set, intersect this space, right? So if you have open set in R2, you intersect. So you can imagine a possible open set in X would be just those interval here, open interval, right? Or union of it, right? So the basis is an open interval either lies on the y equals 1 or y equals minus 1. So essentially, if I code this open interval to be I alpha, then all the possible open set up here is any union of such interval, right? Doesn't matter where the interval lies on which line, right? Any possible union of those interval. Now you want to see that, okay, this is the possible open set in X. Once you go down here, what would be the open set looks like, right? So you can see that, okay, we already know if we want to find out what open set in the quotient space looks like, we need to know what V looks like. V is an open set in X. But we already know V looks like a union of all this interval, whatever the interval is, any size, any length, right? Then what will be U, right? U will be, in this case, it will work because pi is a surjective map. This is actually a more rigorous way to kind of just write it, the proof. So U is essentially the image of all this union of interval under the quotient map. You essentially map it down to through the projection map, right? So, and then even better, you can, because this is a union, you can, by the set theory, right? We can actually take out the union outside. So this means to know what open set U looks like in the quotient space, you only need to know what would be the image of those interval looks like down there. Okay, so now let's see. So let's go back to maybe I draw a new picture down here. So let's say, okay, this is X, 2 lines. And we have distinguished to 0 here, okay? Now go down to pi. We want to see that what will be the image looks like, right? So let's say if you have an interval here, doesn't contain any of the origin, right? It would just map down to some interval here, right? Okay, let me do the 2 origin here, right? This is the quotient space. But the only situation that you want to be careful is that if you have an open interval containing one of the origin, then down here you need to describe it carefully, because then, so if this is the case, let me call this A and B, right, interval. Then if you map down here, then what will be the interval looks like? It will looks like as if from A to 0, union this origin, and then maybe as a equivalent class, right? And then union the remaining of it from the interval from 0 to B. You need to actually specify which origin you're using right now. So that's the open set, another type of open set in the quotient space. And as you can imagine, if you have an open interval containing another origin, then you need to swap the origin to a different one. Yeah. So you know that there are roughly three types of open set in the quotient space. One is this one, if you want to contain the first origin, or this one if you want to contain the other origin, or any other, I don't know, that doesn't contain origin.
Different cases.
So, okay. So contain origin, any origin, any. So now these are the basis, right? So any open set will be the union of those three types, right? So these together are the basis for my quotient space. Any open set should be union of these three types. So you need to know this before you can actually start proving, because you need to know what a typical open set looks like. And actually, this is the key to say that this space is not Hausdorff. Now, can you see it, that why it's not Hausdorff? Where's the problematic point?
Oh, give me one second.
So what's the definition of Hausdorff?
I got it. I need to look at my notes.
Yeah.
Sorry. Jeez. For every pair of distinct points in M, there are disjoint open sets such that P is in U and Q is in V. Well, so the origin?
Yeah, right? Because you want to, so Hausdorff, like roughly geometrically speaking, it means you want to separate two distinct points by disjoint open set, right? But you can see that what's an open, there's only one type of open set that containing the origin, right? You can see that it's either this one, the top or the second one, right?
Yeah.
But then they cannot be disjoint, because other than the origin, you have same thing there, right? Like other than the, so that's why you need to, because before you can even talk about open set, you need to know what a typical open set looks like, right? So so basically that's essentially tells you that, because any open set containing either one of the origin is going to be union of things like type 1 or type 2, and those things are definitely overlap. They're not disjoint, right? So which means you cannot find disjoint open set separate the first and second origin. So that's essentially, so that's why I said that before you can even say the Hausdorff or prove that not Hausdorff, you need to actually realize what an open set looks like in this case. And then from here, you say that, okay, whether it's second countable, you can still prove second countability and locally Euclidean. Yeah. Because locally, it's still really, if you think about it, what this space looks like, right? Okay. It looks like a real line with double origin. That's why they call it line with origin, two origins, right?
Yeah.
So, okay, origin is a little bit tricky, but do you agree with me that locally, if you are picking a point from non-origin, locally, it just really looks like real line?
Yeah.
Right? So now you wonder, okay, then what about at origin? Okay, at origin, it's not too bad because if I'm at this first origin, how could I pick an open set? Then you just kind of ignore this another origin, right?
Yeah.
So it's as if you just like, if you have a real line, right? And then you just move one of the point to the origin, right?
Yeah.
So you still can find an open set that kind of, you need to find a, I mean, this is very rough. What I'm saying is very rough. You need to really write down the correct mapping to some interval in R. But you can see that it doesn't matter. Locally, it will looks like it will be, you can find a map phi such that locally you can find a open set that's homeomorphic to an open set in R. So they are locally homeomorphic to real line. Yeah. So it's not actually R. It's not two-dimensional. It's one-dimensional.
Yeah. Okay.
Yeah.
Yeah, I need to learn how to just draw it out, because
yeah, actually drawing is really, I mean, topology. And then also I'm wondering that, do you have a topology book with you? Because a lot of this you really need to check up some dictionary for some definition or example, something like that. So I'm wondering, do you have any topology book with you?
Yeah. So I think last year I was supposed to take topology with Catherine.
Oh, really?
But
Okay.
then I was scheduled. They overlapped my schedule, my
Okay.
teaching with that class, so I couldn't take it. But I bought the book, so I have
which
that.
one is that? Which topology class? The point set
It
or
was-
actually the algebra topology?
It was the 525.
Okay, perfect. So, okay,
And then and I do have Hatcher. I know you sent the link, but for my thesis I had Catherine gave me Hatcher.
Hatcher may not necessarily work well. I'm trying to think of, because Hatcher might start with something even, Hatcher, I don't remember starting with topology. I mean, in the sense that they probably start with homology and all this more homotopy. Probably, yeah.
Euler characteristics and
yeah,
all that fun stuff.
Here what I need is the point set topology, where the book that you bought with Catherine, I think that is that the book she uses, MS book, like a lecture notes type of thing?
Let me one second. Let me go find it.
It's the link I give to everyone, right? I think they have an online link.
Yeah.
Yeah. So the problem with that link is that if I remember correctly, that book is a lecture notes. Actually, you know what? Let me first stop recording because I feel like
Oh.